a nucleus that is unstable wants to get rid of excess energy, it emits one or more of these kinds of particles. Actually, there are three particles. One is pure energy, and that's the gamma. X-rays are another type of ionizing radiation, but it does not use radioactive sources generally to do that. Okay? If you've been to the dentist, you sit in a chair, they put that nice heavy lead apron on the important parts, and they aim this thing at your mouth, and the technician says, "Don't move, I'll be right back." And then they leave the room and press the button, and you get an X-ray. That's high voltage ionizing radiation to take that X-ray, and it's a minor amount. So why doesn't the technician stay in the room with you? They could have put the button right there.
Because they have to do it repeatedly over and over and over again.
Over and over and over again, day after day after day, and that's a cumulative exposure. Your exposure is one quick, short, done for 6 months or a year. How do we protect against ionizing radiation?
Don't go to the dentist.
I would not advocate not going to the dentist. We can use shielding, that's one way. Alpha particles can be stopped by a thin piece of paper. Okay, so we mentioned radon earlier, right? If you have radon in your home, it doesn't get very far. If you breathe it in and it decays in you, that alpha particle it emits can do some damage. So a simple piece of paper, cloth mask, things like that. Beta particles are a little more energetic. They go through paper, they'll go through skin, but they can be stopped by a sheet of aluminum. Gamma rays can get through both paper and aluminum and typically are stopped by a slab of concrete. However, neutrons, being much more energetic, need lots and lots of water to stop them. Okay? So in the nuclear reactor that Lenora was talking about, there's water, which helps cool things, but there's these neutrons that get emitted in the fission reaction when uranium decays. Neutrons are produced. Those neutrons then hit other uranium, and those uranium decay and produce more neutrons. So it's like a bowling alley, where when you throw the ball down, that's the neutron, and you hit those pins go flying off, more neutrons. And some of them actually land in other alleys, and they knock other pins. And those pins fly off, okay? That's when the reaction runs away, the runaway chain reaction. If we control how many of those neutrons can hit other uranium atoms, we can control that reaction and keep it safe. Okay? So that's what these graphite rods are for, that Lenora was talking about, is to help absorb some of that, plus the water does as well. And we can increase the amount of graphite rod or decrease the amount of graphite rod to increase or decrease the reaction. Did I get that pretty great? Yeah. All right. You mentioned time, distance, and shielding. We just talked about the shielding, different types of shielding. Time, you want to limit the amount of time that you're exposed, like the dental technician, right? You're exposed for a very short amount of time. They will be exposed day after day after day. The distance, you want to be further away. Every time you double the distance, you get 1/4 the amount. Okay, this is true for pretty much everything. So by simply doubling your distance, you've reduced your exposure by 1/4. Tripling your distance, you've reduced your exposure by 1/9. Okay, 10 times the distance, that's 1/100th the exposure. So simply stepping back does a lot of good. The further away you are, the better off you are. So time, distance, and shielding. By the way, this applies for pandemics. Reduce the amount of time that you're exposed to people. Keep 6 feet away and wear a mask. Okay. Some terms, we're going to talk about some terms that you'll come across for radioactivity. Half-life, all right? Half-life is a measure of time. Now, when these things decay, when these radioactive substances decay into other things, there's less of the original substance left. right? So how long do we have to wait until we only have half of what we started with? That's the half-life. Some half-lives are short. Cobalt-60 has a 3-year half-life. Cesium-137 has a 30-year half-life. Okay, so some things last a long, long time as they decay slowly. Other things decay very quickly, and pretty quickly there's very little left of them. Yes.
Here's a good one.
Sure.
If it is a 30-year half-life, its full life is 60 years?
So,
No.
well,
Ah,
here's where it gets a little bit tricky. Now imagine this. Here's a little thought experiment for you. Let's get a shoebox and 100 pennies. Starting with 100 radioactive atoms. And I put them in all heads up, right? Heads up is radioactive. Hasn't decayed yet. I shake the box and I open it up again. What do you think is in there?
Some heads up, some heads down.
Probability says there's about half of them that would have flipped, right? So I take out the tails and I've got half left. Now I shake my box again. That's another half-life. And I look inside, and how many do I have left? About 25, so half of a half. And then another half-life goes by, I shake it again, I've got about 12 or 13. Right, so it doesn't automatically go away after 2 half-lives. It slowly goes away to the point where you have very little left. So how many times do I have to shake that box until I have just 1 penny in there? Does that make sense?
Yeah.
Do they establish that just by observation?
Yeah. And it has to do with decay rates and amount of energy release. There's other factors that go into it. So how do we measure radioactive strength? So there are different units, and these are all scientist names. You familiar with Curie, right? Pierre and Madame Curie. That's our traditional English unit of measure. The international system or the metric unit is a becquerel. So when your subject matter experts start talking to you about this kind of stuff, they will use terms like Curie's or becquerel. These terms measure how active that substance is, how much it decays in a certain amount of time. Is it a lot, or is it just a little? That's the activity. We are surrounded by all types of radiation all day, every day. A lot of the ionizing radiation comes from terrestrial sources. It's in the rocks. It's in your homes. You have granite countertops in your home. So you're probably getting a little bit of exposure because of that granite. Concrete, same sort of thing. It's got aggregate in it, typically granite. Do you fly frequently? You get more exposure to cosmic radiation higher in the atmosphere. And then there are other things that we could do for medical purposes. Right? There are medical uses of radioactive substances for either imaging or controlling cancer, things like that. You can go to the EPA. The EPA has a website. Calculate your radiation dose. And you could put in things like, do you have granite countertops? I fly this many times a year, and other things. There's a bunch of questions, and you can see just how much radiation exposure you have. The maximum permissible limit is 5 rem. We'll talk about rem in a second. Most people have less than 1 rem in a year. So 0.6, 0.7. So it's pervasive. Can't get away from it. So what are the effects on the body? Well, it depends on how it gets in. We talked about routes of exposure. What are the routes of exposure? Ingestion, injection, inhalation, and absorption, exactly. So depending on how it gets in. The problem is at the cellular level. We mentioned ionizing radiation causes water, H2O, to become H2O2. peroxide, which is bad for cells. In addition, some higher energy stuff like gamma can cause changes to DNA. Most people, adults, can get a dose of radiation and it doesn't matter. We replace cells in our body all the time. But the cells that get affected that are young, maturing cells, if you've got a newborn, an infant, they're growing a lot. Their cells are reproducing a lot. If you've got impact to bone marrow, which produces blood cells, those are immature cells. They will be more affected. So depending on what kind of cells we're talking about, skin cells, everybody grows new skin and we slough it off very readily. Okay? So cells that divide rapidly or currently in the process of dividing would be more affected by radiation. We talked about some of those harmful effects, but there are some benefits to radiation I mentioned before. Imaging. Has anybody ever had an imaging done? Yeah. My wife recently had repaired to her meniscus in her knee, and they did a little shot of dye, and it helps us see different things in the knee where scarring tissue is forming versus healthy tissue, that kind of thing. If you have some of these procedures done, they might actually give you a card that says you had a medical diagnostic imaging and radioactive stuff is now in you, in case you want to go to the airport and go through TSA and the alarm goes off because you're radioactive now. It only lasts a few days. We actually had in Connecticut an older woman on the highway get pulled over by the state police because they have sensors on their vehicles. Their trooper sensor went off and pulled her over. She had had a procedure. So, funny story.
McCarran Airport in Vegas, people go out to the test sites
Oh, yeah.
and then come in with dirt all over their shoes, and they're always getting pulled over by TSA, pulled out of the line, and particularly people who go out for, like us, who go out for work and they stomp around the test site.
Yeah.
They'll end up with radioactive stuff, soil on their shoes and things.
You definitely want to clean your shoes and wash your clothes. We talked a little bit about chronic dose, small doses over time. That's your X-ray technician, right? That's your normal everyday exposure to stuff. An acute dose is a very large exposure in a very short amount of time. Both do harm to cells. This will do much more harm much more quickly and could cause something called acute radiation syndrome, or ARS. The initial symptoms of ARS are much like flu symptoms. Okay. Eventually, you'll start getting other things showing burn type injuries on the skin. You'll have boils, things, nasty stuff. So if you have an exposure, it might not show immediately in some of these more severe ways. It just might be fatigue, diarrhea, things like that. You might confuse that with a cold. What historical events can you think of where there might have been an acute exposure? Chernobyl, yep.
Island, 3 Mile Island.
Interestingly enough, 3 Mile Island did not release any significant amount, although it was widely covered in the media. That's a whole story for the PIO class. A lot learned from that. So Chernobyl, yes. Fukushima Daiichi, right? Because of the tsunami. Lenore talked about the tsunami. Any others?
Hiroshima.
Hiroshima, Nagasaki, all of those, yes.
You got any of those
Exactly.
Milwaukee?
Exactly.